So hello everybody, we are back again to our class. Now what we are dealing with this generalized Ohm's law, and we are trying to model the collisional term in this case because we had no other way to escape from that, and we have modeled it as this collisional term as minus rho me by mi sigma and j, and we have reached this expression from a dimensional analysis, and we have explained in detail. Now what we will do, we will try to reduce the expression. So what we had earlier, that this expression was there with us, so del J del D is equal to this one, and we had planned to replace this term and this term using the expression that we have just arrived, that is k will be replacing by this one, and e square ne by me into v term will be replacing by these two terms. So exactly this equation will be taken into our next slide, and we will replace this by these two terms and this one by this term. We come back. Now here we have replaced this term by these two terms, and this is the model of k that we have used, and we are now simplifying. So this is del j by del t is equal to this term comes when we this term and this term adds up. So that give you basically the total pressure. So you know that PE and PI, they are additive, and that adds up and gives you the total pressure P, and then these two terms they adds up, and then you know that ME NE plus MI NI, so that should give you the mass density actually is square then rho m by me mi. Now here you should know that this Ne and Ni, they are having the same value when they are fully ionized plasma. So when you multiply these two, and then Me plus Mi Ni gives you the mass density, and then here you come Me Mi at the bottom. So you finally get this term as square rho m by Me Mi, and then multiplied by E, and then this term comes as minus of E by Me into J cross B, and this term comes as square by Me Mi into rho m into V, okay, cross B. And the other term, this one is rho m E by Mi into sigma, and then E by Me. Now here one thing we have done actually, you see that we have not used this term mi. When you are dividing this by mi, this term is not there, and then when you are comparing this term E by me and E by mi, that the relative importance of this term is insignificant, because mass of ion is much higher than that of electrons. So when you do that, then only this term you can keep for approximation, and that is exactly what we have done. E by me is over here, and this term is coming here. The other one, that this rho m is there, then this one actually, because you know that same thing, whenever we are dividing something by mi and we are dividing something by me, then relative importance of the term of this term becomes very less compared to the other term, so we can neglect that one. So exactly that the same thing we have done over here. So this is B cross B, and then this is the term. Now what we are essentially getting, you see that this is your square over E by Me into Mi, then minus E by Me into J cross B plus E square by Me into Mi, and then rho m into B cross B. So, and the last term is giving this one. So we can bit rearrange. So these terms are remaining as it is, but you know, when you are going for this term, let us write it as rho m square by Me into Mi. So we put that in bracket, and you can notice that the same term we have achieved in case of E also. So is k square into rho m by Me Mi, and then this collisional term also resulting in the same coefficient. You see here, there is rho m E. Actually E over here and E over here, so they multiplies and forms E square, and then rho m is there, and then me mi into j by sigma. Okay, so what we are getting here now, del j del t is equal to E by twice me, then same factor appearing over three places, here, here and here. So if we multiply the reverse of this on either side, then these terms will, these factors will go and we will be left with a much better looking equation. So what we will get, me mi by rho m square, we have multiplied by inverse of this coefficient. So this factor is coming over here, and then this one, this me is getting cancelled by this me, and you know that E is there and here E square is there, so one E is cancelling, only you are getting E, rho m into E, and this two factor is coming over here, and mi is on the top, me got cancelled. So I am getting now mi by twice rho m into E into grad P plus, then this one is giving you E because this inverse factor has been multiplied, so bare E is coming, and this is you know that this one is V cross B. Which one? This one. This one is coming as V cross B, and this term again you are multiplying by E by ME, so you will get similar except this factor 2. So MI by rho ME you are getting over here, and then J cross B. This term is now shifted over here after this term. So this is MI by rho M into J cross B, and then last one, because we have multiplied by the inverse factor, so this goes, and you are left with bare J by sigma. So the expression just now you have got is called the generalized Ohm's law in case of plasma. So what it relates? It relates the time variation of J with grad P, electric field, then motion through V cross B, and then the current density and the conductivity. So it is an ideal case for you know this plasma, which can associate each of these. So it can have this magnetic field, it can have electric field, it can gradient of pressure, and it can have time variation of the current density, all these things together. Then how the current density will depend on all these things, that basically gives you a law which we tell as the generalized Ohm's law in case of plasma. Now coming to the reduction, whether we can reduce it to ordinary Ohm's law. Now you see that suppose we are having a steady current in a plasma, so there is no variation of this current density, so you are getting this term del G del T equal to 0. So this term is 0. Then suppose you are having a plasma which is at uniform pressure. It is quite possible in many of the plasma where the gradient in pressure is 0, and then this term goes, and then what you are having that V cross B is you know that much greater than Mi by rho m E into J cross B. Then you can neglect this term compared to this term, and then finally what you are left with, this is 0, this is 0, E is there, then V cross B there, and then this one minus J by sigma is there. And what finally you are getting, this is our very familiar form of the Ohm's law, that is J is equal to sigma E plus V cross B. So under this special condition, we are able to retrieve back our known form of this Ohm's law, that is J is equal to sigma E plus V cross B. And if it is not so, and the plasma is complex as usual, this is the form which will be generally valid. Also, you should remember that we have done number of approximations in reaching this nice form, and those approximations was valid for most of the cases, but there may be cases where those approximations may not be very accurate approximations. So those cases we need to consider depending on case to case, but these are generally the forms of Ohm's law that you can find in case of plasma. So this is the general one, and under certain cases you can reduce it to the conventional form of this Ohm's law. So far in the fluid model, what we have now arrived is mass conservation equation. We had one equation. Charge conservation equation, we have one equation. Then momentum conservation equation, we have three. Generalized Ohm's law, three. And then we have the Maxwell's equation. Curl E is equal to minus del V del T, and curl B is equal to mu 0 J plus mu 0 epsilon 0 delta E delta T. So you can see the, I have written in the bracket how many equations you can get from there based on the components actually. So these are vector equations, so you are getting 3 components from each, and these are scalar equations, so you are getting 1 from each. So what here total you have got? You have got 3 plus 3 plus 3, 9 plus 3, 12 and 2, 14. And how many total number unknowns here? So you have rho m and rho c 1 1, and then your this is velocity 3 components, j 3 components, electric field 3 components, and magnetic field 3 components. So if you add them up, you see that you are also number of unknowns are 14. So you have total of 14 equations and you have 14 unknowns. So this set of equations are exactly solvable equations, and they are called the MHD equations. Now to be a bit explicit, let me write the MHD equations, how they look. So these are the MHD equations. So you have, this is for the mass conservation equation, this is for the charge conservation equation, this is for the your momentum conservation equation, and these two are taken from the Maxwell's equation. So these are the this set of equations are called MHD equations. MHD stands for magneto-hydrodynamic. So whenever somebody says that this is the magneto-hydrodynamic equations, they essentially refer to this kind of set of equations which together can explain the behavior of the plasma under magneto-hydrodynamic conditions. Now these are cases which are generally valid, and these general MHD equations can lead to some ideal MHD equations under the conditions that, when the conductivity is infinite, your very low frequency phenomena are important, and no charge imbalance is there. So this essentially tell you when it is conductivity is infinite. So how it comes over here? Then I should go back that J is equal to your sigma E plus V cross B. You say that conductivity is infinite, then what goes? It goes on the left side as a denominator, and sigma is infinite, so this term becomes 0. So you get E plus V cross B equal to 0. This is exactly the thing that E is equal to minus V cross B. Okay, and as I told you that your no charge imbalance, so rho c is equal to 0, and then this your time varying components are extremely low frequency one, that is delta E delta T close to 0, but it is not exactly 0. Okay, now we come to this thing how they can be reduced. So this equation remains like this. Now we are telling that ideal MHD equations has no charge imbalance, so rho c we can put 0 over here, then it is reducing to divergence J equal to 0. And the third equation, when rho c you are putting 0, so this grad p term is there, and then J cross B term is there, and this is there, and then curl E equal to minus del B del T. Okay, now we have got E equal to minus B cross B, so we put over here. So then this negative sign from here and this negative sign they cancels, and you get this equation reduced to curl of B cross B equal to del B del T. Now remaining the last one, curl B equal to mu 0 J plus mu 0 epsilon 0 delta E delta T. What you can see over here, see what we have put here, curl equal to minus del B del T. We are not neglecting del B del T over here, but here you see that del E del T is a small quantity, and when you are considering with this first term mu 0 J, this term is contributing really insignificantly. So in that case we can put that curl be equal to mu 0 j. It is a good approximation. So these are the your general image equations, and under ideal conditions this can reach to this ideal image equations like this set of equations. So you are now clear that what are the image equations, what their general form, and what are the ideal imagery equations. And as we have seen that each of these equations so far we have derived. Okay, so from the very basic things, and each and every term we now understand what they means. Now I will come to some application of this fluid model. They are very interesting. Now you know that when they are having finite conductivity, you know, this plasma that you generate in laboratory, they are having of course finite conductivity, and they offer substantial amount of resistance. So what happens there actually when the conductivity is finite, and these implications, right, the conclusion that we reach from this kind of study, they are actually valid in many of the applications that we encounter in our processing plasmas, and your, you know, the various devices when you try to operate them. These things play there, so their effect there, and that's why we should know the kind of behavior that we may get there when this kind of situation arises. So neither anything is having infinite conductivity, and not that your zero conductivity. So somewhere in between many of the times we face, and how the plasma will behave, because plasma associates your electric and magnetic field, how they will behave in such situation, we can get some good idea from this study of this kind of special cases. So the first one is finite conductivity and steady electric field, and we want to study the diffusion of magnetic field in such plasma, if any. Now what we get, you know that the Maxwell's equation, what it gives curl B equal to mu 0 into J. Now J is equal to sigma E plus V cross B, and we have told that sigma is finite. Okay, so we have some appreciable value of sigma. Now you know curl of E is equal to minus del B del T always valid. So you take curl of these equations on both sides, then what you get, curl of B is equal to mu 0 sigma, then curl of E, and then mu 0 sigma curl of V cross B. Okay, then what we are telling you that for stationary plasma we have this no moving component, so the plasma is not moving as a whole, so we can take that B is equal to 0. So this equation then results in del B del T equal to 1 by mu 0 sigma into del square B. This is a very standard form of diffusion equation, and we know that it has a solution of the type B equal to B0 exponential minus T by mu 0 sigma into L square, where L is the your length scale of the spatial variation of B. Okay, and B0 is the field at T equal to 0. So now what is the diffusivity is 1 by mu 0 sigma. So this is called the diffusivity, and the diffusion time is mu 0 sigma into L square. So because this is exponential minus T by tau, tau becomes the diffusion time, and here it is tau is equal to mu 0 sigma into del square, because by this time B0 reduces to 1 by E. Okay, so T when becomes equal with this, then it is a minus 1, so B0 by E. So that is the diffusion time, and it is here is mu 0 sigma into L square. So if plasma wants to get diffused away, the diffusion time depends on the sigma as well as length scale of the plasma. So if this plasma is a large volume plasma, it will take more time to diffuse away, and if conductivity is very poor, then it will take more time, but conductivity is high, then it is diffuse away very quickly. So what we see that if the conductivity is finite, in that case what happens, the plasma diffuses away. Plasma diffuses away with a diffusivity of 1 by mu 0 sigma. This magnetic field, basically this is the diffusion of magnetic fields. So magnetic field diffuses away with a diffusivity of 1 by mu 0 sigma, and diffusion type of mu 0 sigma into L square. So this is the diffusion of magnetic field. So in a finite conductivity plasma where sigma is finite, then the magnetic field inside the plasma diffuses away. The diffusion time depends on the length scale of the plasma and conductivity of the plasma, and the diffusivity is 1 by mu 0 sigma. So now I come to the other part, when the conductivity is very high, and for all practical purpose we assume that the conductivity is infinite kind of thing, and in that case we will see that the magnetic field get frozen inside the plasma. Wherever the plasma goes, the magnetic field goes with it. If it bends, the magnetic field also bends. If it moves up, magnetic field also moves up. Like that, the magnetic field is frozen inside the plasma. Where the plasma goes, the magnetic field also goes with it. Okay. So, when the charged particles are moving, like that solar storm. Solar storm, what is that? The ionized particles from the sun is rushing towards the earth. But when they are moving, they are carrying with that the magnetic field of sun. So that is how the solar storm not only includes the charged particles, together with it, it includes the magnetic field that is carried from the sun to earth. And that magnetic field collides with the earth's magnetic field. And so why actually earth's magnetic field is very much required to protect the environment of earth. So this consideration that it is having infinite conductivity, this basically tells you the how the magnetic fields get frozen in such conditions. You know that J equal to sigma E plus B cross B, we have seen from our imaged equations, and then when sigma becomes infinite, then this term E plus B cross B is 0 and E becomes minus of B cross B. Then the Maxwell's equation, what it gives? It gives del B del T is equal to minus of curl of E. Then E we put over here, that B cross B. And then what we get, that this minus sign becomes positive over here, and then curl of V cross B. Now what we will do, the flux of the normal component of the magnetic field integrated over the surface inside the plasma, that gives del B del T dot N dot ds. So it is telling that the normal of your surface, and then B dot this, so it gives you the flux basically del phi by del T. So this flux is coming to be curl of V cross B dot N dot ds. Now we apply the Stokes law. So then what will happen? Then this surface integral get reduced to this line integral, and you can write it as integral of V cross B dot TL. And if you use the vector identities, then you can write this as B dot dl cross V. So what we are getting now, d phi dt is equal to integral of B dot dl cross V. Now what this actually signifies? So this is d phi dt is the change in flux, and what is giving that B dot dl cross V, that is equal to. Now this dl cross V, dl is this is the loop, and V is this velocity, and if you say dl cross B, this is dl cross V, this is basically gives you this area. This is dl, and then this cross B, which will be perpendicular to both dl and the B vector, so it is normal. So this is basically describing an area which is described by a small moment of this thing. This is the dl cross B. Now B dot dl cross B, this basically represents the magnetic flux phi associated with this increased area. Now d phi dt represents the rate of change of flux. So this is equivalent to saying that the change in flux is basically the flux whichever is going out because of this expansion. So as the area S expands or contracts due to mhd motion, the same field lines get redistributed over the expanded or contracted area. And in the above picture, suppose we say that S doesn't expand or contract. So S is moving like S only, like a cylinder, but it can move bent. But here then we see that dl cross V, this is equal to 0 because this V is this side, and dl cross V would be exactly perpendicular to B, not 0. dl cross B will be exactly perpendicular to B, and then B dot dl cross B, this one, it will be 0. So it means that d phi dt would be 0. So if d phi dt is 0, this means that flux is constant. So that is what exactly this expression, that change in flux d phi dt equal to the your B dot dl cross B, exactly the condition of frozen field lines. When this condition actually meets, this exactly the condition for frozen field lines. And when you just see that when S doesn't expand, then B dot dl cross B is exactly 0 and d phi dt equals 0, that you can understand that even though the V is there, this flux is constant. So when the conductivity is infinite or very large, we can assume that the magnetic field are frozen in the plasma. Wherever the plasma goes, the magnetic field also goes with it. Now we'll come back to the last part of our fluid model, where we should take actually the second order moment of the plasma kinetic equation to reach the energy equation. And you have already seen that even the first order moment, where we obtain your momentum conservation equation, the mathematics was pretty complex. And what we are interested in this course is that we want to bring insight into the problem. We want to understand the behavior of the plasma system rather than to get lost in the mathematical complexity. So that is why, because of the complexity of mathematics for taking the second order moment is pretty high, and these are available in some of the plasma textbooks. So I am not going into that, because for processing plasmas, thermal and your cold plasmas, we really don't need that much of mathematical complexity. We are very well focused on the application part. We need to know the mathematics, the underlying principles, how the plasma system will behave in a more physical manner rather than entering into the mathematical complexities. So we will derive this energy conservation equation in a phenomenological manner without going into mathematical details of complex derivations, but we will not miss any of the physical aspects of the mathematics that will be lying there. Okay. So in our next class, we will be going for this energy conservation equation in fluid model. Thank you.